is this ice. This ice has been sitting in a bucket of water for a half hour, right? What is happening to this ice?
Slowly melting.
Slowly melting. Okay, so melting is an example of a phase change. What are some others? What's the opposite of melting?
Becoming gas.
Okay, depending on how you look at it. So melting and freezing, they happen at the same temperature, right? All of this ice water will be 0 degrees Celsius the whole time until the last bit of ice is melted, as long as we keep it stirred. If we don't stir, we might get pockets of different temperatures. And if I put this in the freezer until the last bit of water was frozen into ice, it would remain at 0 degrees Celsius, even if the temperature of the freezer was much colder. So during a phase change, you don't have a temperature change at all. That's a key point for this lab. That's essentially the key point of this lab. That during a phase change, you don't have a temperature change. What are other phase changes?
Becoming a gas.
Okay, so maybe boiling. Sublimating, that's another way to become a gas. It's not one you see frequently, but what is sublimating? Anyone? Okay, so if you have a big brick of dry ice, and it's a solid,
gas.
right? It's solid carbon dioxide. It sublimates. It just goes straight from brick of ice to gas because it's so cold and the room is so warm, assuming it's at room temperature. So it never puddles into a liquid and then becomes a gas. It sublimates straight from solid to gaseous phase. And then, of course, sublimating, though, it will throw in confusion. We don't want to do that. So boiling, and what's the opposite of boiling? If something goes from gas to liquid.
Condensing.
Condensing. Okay, so these are the major phase changes that we're going to be looking at this year. Melting and freezing, boiling and condensing. So if I boil some water, which I should probably set up, if I boil some water, then just like I said for ice and freezing, during a phase change you will not see a temperature change. So water boils at what temperature? Oh, there it is.
100 degrees Celsius.
100.0 Celsius. Of course, if our water is contaminated at all, it will boil a little higher, and I'll teach you about that later in the year. But take my word, it will be a little hotter as it boils if it's contaminated. But whatever the temperature at which it boils, it will not change temperature during the boiling process. So it will stay, we'll assume 100.0 degrees Celsius, I'll turn this, the whole time that it's boiling, until every bit of the liquid water has become a gas. Key point for the lab. So, what we're going to do is everyone's going to start with a beaker of ice water. This is possibly the most boring lab you'll ever do in your lives. We're going to watch ice melt. But you'll start with your ice water. I'm actually going to crush it up in hopes that that will speed it up, because sometimes this lab takes forever. And then you'll stir constantly, because if it's not continuously stirred, then the bottom part that's touching the warm table might get a little warmer. So you have to stir. We're going to take a temperature reading every 30 seconds, which is chaotic. So don't be surprised. So what you really want to do is to have your paper laid out, your pencil. You want to put away like the majority of your stuff, your textbook, your phone, because you don't want to spill on your phone. And then while you're stirring, in case you slosh stuff here and there, you don't want to spill on stuff you like. So you want your piece of paper out. We're going to take a data point every 30 seconds, which means we'll acquire a large number of data points pretty fast while the ice is melting. So our ice is melting, What do you expect to see as the ice is melting? Temperature
Kind of
shouldn't
spoiled
change.
it already, so.
Yes, and I'm spoiling it on purpose, because when you get into the chaos of taking the reading, writing down the reading, keeping it stirring, all that, I don't want you to lose sight of the big point to just do the lab. So the big point is it's not gonna change temperature, I hope, as long as we keep it well mixed. So a source of error here would be, we're not mixing well enough, yeah, that could happen. Also, the glass can get a little bit colder than the ice water. So if you're taking a temperature, here's the wrong way to take a temperature. Touching the glass gives you a wrong reading, okay? So when you're stirring, and you should stir with a stirring rod and take a temperature with a thermometer, but that gets even more chaotic and we end up spilling with things sticking out. So you want to stir, but not like be banging my thermometer against the glass and then cooling it off or heating it up by touching stuff with it. So you really want to try to keep it moving without a whole lot of banging. Plus, when 6 different thermometers are banging, it gets really like, ooh, by the end of it. So once we get all of our ice melted and we observe our temperature change, or hopefully no temperature change, then I'm going to take over. I'll take somebody's beaker and we'll start to heat it up, and we'll watch as the temperature rises until the boiling point. Once it reaches the boiling point, what would we expect?
To not change anymore?
Yep, we expect to get to right around 100 degrees Celsius and then not change. So here are some big lab tips. Read the Celsius side of the thermometer, not the Fahrenheit side of the thermometer. Don't occasionally forget and read the wrong side and think your temperature just changed a whole bunch. Make sure you're always reading the Celsius side. So when I pass them out, get a good look at your thermometer, make sure you know what you're doing. When I say like 5 seconds, you'll need to get a reading. If we miss a 30-second interval, we'll just leave it blank, move on to the next 30-second interval. So that'll probably happen, but don't panic, we'll get plenty of
How many
it.
30-second intervals are we gonna have,
Until the
roughly?
ice melts.
Okay, that's right.
So hopefully about 7 minutes of that, and then to boil, probably 7 more minutes. It might go, we've had it take a half hour, sometimes it gets long and irritating, but I promise you, if you don't actually see water not change as the phase change happens, if you don't see that for yourself and then you don't see the temperature, if you don't see that the temperature doesn't change while it's boiling, you won't believe it for real. Like you'll remember forever if you actually have to do this lab, so it does work out for you. So let's do some kind of pre-writing on this lab, because also you're new at writing lab reports in my preferred style. So we want to make sure that you feel prepared and you have this. So this might be a lab report that you're going to want to type, but we want to write some of it together. What's the first thing that we'd write for a lab report?
Objective.
Our objective. Okay, so this lab's going to have 2 objectives. Maybe we'll get rid of that. And we always start with 2 and then a nice strong verb. So what do you think one of our objectives would be here?
Prove that temperature doesn't change during the phase.
Good, and we're going to say observe because prove is a hot button word in science. We can't actually prove anything, as Dr. Weil mentions over and over. But I don't love the verb observe, but we really are watching ice melt today. Observe, so that's kind of what it is. So we're going to observe the temperature. Don't use abbreviations in your lab report like temp, but it's way above my head. So one of the objectives in the lab, as it's written in the textbook, which I've pretty well given up on, is to calibrate your thermometer. And what that means is to see how far off, how imprecise, or I guess inaccurate your thermometer actually is. And if you have distilled water with distilled water ice, then you should see a 0.0 reading for freezing, a mixture of ice and water, and a 100.0 reading for boiling water. But this ice is not distilled water. The water is probably not even distilled water. So calibrating our thermometer is kind of pointless, and they're all very good anyway. They're within 2 degrees Celsius of 0 every year. And then it's hard to keep track of which thermometer had which one and then account for that during labs. It's really irritating. So we're just assuming our thermometers are good. So that objective is not going to be there, even though when you read it in the book, you'll see that. We're not worrying about our thermometers here. And then, well, the other objective would be to measure the freezing and boiling point of water. I'm not actually even interested in that. Let's leave it at one objective. You'll definitely be recording the freezing and boiling point of water repeatedly today, hopefully. So, what's the next section of our lab?
Procedure.
Procedure. So, I am actually gonna leave the procedure to you guys today to try to write yourself. But we'll talk a little bit about how you should do. So, all procedures should be written in the past tense, not I am blah, 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 but I did, you know, the past tense. They should be in the third person, so no I, but the beaker was filled with ice. Not I filled the beaker, not fill up the beaker, but the beaker was filled with ice. So you want to, everything that gets done for your lab setup, you want to record in your procedure. So leave a space. I would say, I don't know if I have a copy of kind of last year's procedure or something. Probably leave 8 lines so that you can write it down and you'll type it up or rewrite it or, you know, turn in your spilled all over copy and see what happens. But hopefully you're gonna make a new copy of this because it could get messy. So everything you do, make sure you write a procedure step. Lab groups help each other remember, oh, we just did something, let's write that down in the 30 seconds between data points. You also don't have to write, a data point was taken. A data point was taken. When, you know, until all the ice melted, the temperature was recorded every 30 seconds. That'll do, just one step there. So let's see. Make a place to write your data after you leave like 8 lines for your procedure. And probably 4 columns of data is going to happen. You're going to make a graph of your data at the end. If you have graph paper, you don't need to get it out because it'll be too chaotic to try to graph it as you go. Let me think. So if you have some graph paper, you're going to have lots of time data points, and you know what your temperature data points are going to be. Like probably you're not ever going to see a temperature less than -5 degrees Celsius. I don't think you'll see negative temperatures, but I guess it's possible if your thermometer is inaccurate in the other direction. You're probably not going to see a temperature bigger than 105 degrees Celsius. Water boiling is generally around here, lower than 100 degrees Celsius. So your range on the y-axis is going to be this at the absolute maximum. Your time, of course, we can't predict, so we can't kind of draw in the graph and then fill it in. But, I mean, you'll probably make, you know, 1 minute hash marks or 5 minute hash marks, but then you'll have points in between for every 30 seconds. And we'll see how long it takes. But you'll definitely want to graph it. You need to label your axes. So when you graph, you're going to label your axes. So temp, and then your units, degrees Celsius. And then you have to keep your scale constant. So you can't just say, oh, well, I didn't get any readings between 50 and 70, so I'll just go 40, 70. You know, you have to have every 10 degrees or every 5 degrees, and they have to be even. So it'd be like -5, 0, 5, 10, 15. You can't just skip 20 and go into 25 because you didn't have any data in there. They have to be evenly spaced. Time also, you know, if you're going by minute, 1 minute, 2 minute, 3 minute, 4 minute, if you don't have enough lines on your graph paper for how long this lab takes, then you might have to go 2 minutes and then just say, I've got 30-second intervals between there. But once you know how long it takes, you'll be able to set up your axes. So you'll write time, and then you'll write in minutes or in seconds or whatever you're drawing. I'm assuming it will be in minutes. So you'll graph at home unless we have ample extra time at the end of class, which never happens. Let's see. Okay. Set up graph, discuss theory, sources of error. Sources of error, big one is not stirring thoroughly. There's one at the point where we switch from you guys having your ice melted to me taking one of your beakers and starting to heat it up. You know, just when a lab changes hands or something that can be, but it's pretty okay. Oh, and here's a question that doesn't have to be part of your lab report, but is a test question that can trip people up. Okay, so let's say I want to cook food at a constant temperature. Why is boiling a good method for that?
Because the phase changes, the temperature is constant during the phase change.
Right, so that boiling water will keep that food at a very constant temperature because boiling water doesn't change temperature while it's boiling. Steam can get hotter than 100 degrees Celsius, but water in its liquid form can't. How about, let's say, like yesterday I roasted a pan of zucchini. So I sliced it up, put it in the oven, and I roasted it. How hot do you think the aluminum cookie sheet got?
So how does it?
Yes, so if the oven was 350, the cookie sheet got to 350. How hot did the zucchini pieces get?
So how does the cookie sheet?
Okay, so no. And here's another area where phase change is very interesting. Because zucchini is so much mostly made of water, until you have absolutely desiccated, boiled all the water out of that zucchini and you just have a break of charcoal, which totally happens at my house sometimes. But as long as there's any water left in that zucchini and that hasn't boiled away, you're at 100 degrees Celsius for the zucchini. So your pan can be very hot, your oven can be very hot, but your food, as long as it still contains water at all, is going to stay 100 degrees Celsius. So that's just interesting stuff to know for the test that you could make a note of, just so in 2 weeks you don't forget when you take the test and you know that stuff. So I'm going to grind up some ice because I really think that if we have it ground up, it's going to go faster. You guys can pass. So this is a beaker, just so we have lab terminology, beaker, thermometer. Check out your thermometer so you know which one is the Celsius. So U3, 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 and U3. Let's see, I have a beaker, you guys need a beaker. This is a ring stand. It has a wire mesh gauze, probably asbestos, which I don't know, maybe they've changed and used something that's not horrible. It used to be asbestos. And then a ring on a ring stand, which can hold my thing in the fire. Graduated cylinder, which I don't think we're going to use today. And these are just tongs, so if my beaker starts to slip, I can try to seize it before it makes a mess and spills everywhere. Okay, so grind up ice. Hopefully nobody gets mad at me for the noise here, but I really do think it's going to go better if we do it this way. So, yeah, it will be.
It's dripping.
Yeah. I'm okay with that. Okay. So we got nice cold water, cold ice. So any mixture, any amount, tiny bit of ice, lots of water, tiny bit of water, lots of ice, should stay at freezing point, 0 degrees Celsius. So I'm gonna trade you guys. So you guys can stick your thermometer in and then write this first or second or third procedure step. I really hope they don't come to check on me. What's going on in there?
Again.
Oh, Erin, can you pass out the lab goggles? We don't need to put them on until I light the burner, but God forbid when the burner's lit. Okay. stick in your thermometer and start stirring, taking readings, let the thermometer be
Okay, you said to not let the thermometer touch the glass.
No, you should stir or take turns when someone gets tired, someone else.
So are we supposed to hold it like?
Yep, you should hold and stir, because you need to stir thoroughly.
I will take the ridiculous. Which is
Thank you.
I'm going scuba diving.
I got your
When do we start taking temperatures?
As soon as I get everybody passed out here, I'll start the 30-second timer. Okay, so kids, stick your thermometer in, no friction.
Let's see, what's the bottom?
All right, so once your thermometer kind of gets in there and
Keep it around.
You got -1 right there.
I'll clean up my mess and then we'll start.
Should I get paper towels or something?
Oh, I have some. I knew I'd make a mess today, and in physical science, I plan on making another mess. But at least it's just water, it won't hurt the carpet in the long run, right? Okay, so I'm gonna start timing. You be ready to write down a data point in, oh, no way. It's dead, it's lasted so many years, which is why it's dead, I guess. All right, let's try this one.
What's it say?
Okay, stopwatch. So every.
Barely above.
Okay, so take your
0.
first reading. Make sure you know how to get the Celsius side of your thermometer. Get your eye down on the level with
It's
it.
right at 0.
Everyone sees your
write that down
first
first?
reading. Keep stirring, keep stirring, keep
Just a
stirring.
little bit closer.
All right, so write down your first reading now.
Put it right at 0.
Stir, 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 stir.
If you want, I'll write it down.
Like, where are we writing this?
On your paper, just like you're gonna make a big column of many numbers. So, you'll take a reading in 5 seconds. Ooh, it stopped going. Okay, now,
Is it a 10? Yeah, so like this is 0.
take a reading.
This is negative 10. Oh, okay.
It's still at 0.
So we're just making a column, right?
You just need a column, and then
Alright, how
just
about
keep
after every
recording
2 weeks?
until all your ice has been melted for a couple minutes.
Try to keep your hand maybe at the top more so it doesn't heat up the thermometer.
5 seconds to get your eyeball down there, and keep stirring, take a reading now.
Still haven't changed.
It shouldn't change, so that's good. Keep stirring, you want it well stirred. You guys are much quieter at stirring than past classes so far. But when you get tired, it gets harder. And if you get tired, feel free to change off with your friends.
Every 2 will switch.
Now, take a reading now. I didn't give you a 5-second warning there, but
Still, I would say it's a.
sorry.
I wish we could just sit with this. That'd be cheaper. You want me to do it? I'm not out.
Kind of pull it closer. Sorry, can you see this? Kind of put it a teeny bit closer to the 1. Like 8? Yeah.
5 seconds. Take a reading now. Keep stirring.
Good as that?
Is anyone way off of 0 at all? Really stir it.
We got 5 zeros so far.
The lab help sheet says you should have more than one objective, but I'm okay with the one. I might just have to change that, but I'll definitely change it for you guys. See how it goes here. Oh, I think we missed one, so put a hole in your data for that data point. I was looking at the laptop sheet. That's okay, because probably nothing will happen. 5 seconds. And take a reading now.
Still haven't changed.
Right at 0.
Very close.
Think actually so. Come over here.
I'm getting a burn through.
My hair.
Maybe.
So we should have like 6 readings. So we missed
Oh,
1, 10.
I missed another one. I'm really not on the ball today. Draw a line on the next data point. Wow. So are you actually filming? I can like point at someone's speaker. It's really boring watching me put my hair up. Okay, 5 seconds. And take a reading now.
Right at 0 again.
Yes.
Okay, so I'm gonna stop the video.